Actually, I have a quick enterprise DB story to tell you. We've been patent partners of EDB for a while. 2 years ago, the CEO of Infor came and approached us. Infor is the third largest ERP company on the planet. Their CEO is a guy named Charles Phillips. He was the guy who was responsible at Oracle for their acquisition strategy that got them into the application space. And so he knew what it was like for Oracle to have lock-in of their development system. As the Infor CEO, he approached Red Hat and he said, please help us remove our dependency on proprietary infrastructure stack. And we partnered up with Enterprise DB to replace operating system, database layer, and virtualization layer with open source componentry. Postgres plus Advanced Server, Red Hat Enterprise Virtualization, Red Hat Enterprise Linux. We have charts that show we saved a huge amount of cost out of the application, and Infor LM certified and started selling that application. Nice partnership. They did a great job with software that was 20 years old that had deep dependencies on Oracle. We were able to migrate those over. It's good stuff. Thanks very much. So, I am the technology director for Red Hat's Global Partners and Alliances organization. Welcome today. And nodes on that network. And that handful became a dozen, and that dozen became about 30, and that 30 became a couple hundred. And you know the rest of the story. Client-server computing revolution, the whole industry started. And that led to tens of millions, or probably a couple hundred million computers are on the internet. And those computers are mainframes, servers, workstations, PCs, laptops, computers as we know them today. We all know the story. The next wave, though, is when you put devices like this, like smartphones on it. And not just smartphones, but devices like this. You see this is my activity tracker. Raise your hand if you have an activity tracker on you, like a Fitbit or Night Visual or something like that. Yeah. So the thing about these devices is that they're sensor-based. They, more so than computer workstations or servers, they're built to transmit telemetry across the network. When you connect them to a network, a couple things happen. They generate huge amounts of data, and they also don't always generate data reliably. So this guy's pretty reliable. He's on a network, he's fine. This guy generates data and mostly sends it to this guy. And he's connected through a Bluetooth connection and only intermittently. He's not on the network all the time. So that's to save power. When you start looking at the next level of devices that are on the internet or on a network, you're talking about a couple of things. 3 orders of magnitude more devices. So going from a couple hundred million to tens of billions of devices on the internet. I think you heard Lungo earlier today in the main session talking about that. Also, these devices are unreliable in a couple of ways. Like I said, they're characterized by intermittent connections to the network. They're not always connected, so it's harder for us to think about reading data from them. And also, depending on the device, the data itself may not be reliable. If you all remember the RFID phase from 10 years ago, the thing about RFID is those tags, it was hard to sense and read the data off the tag. You often had to do it multiple times in order to get a solid read. Data just aren't always reliable first time out. So there's a tremendous opportunity with the Internet of Things. The kind of information you get from here is amazing, but you have to be careful about how you do it, or you can be just drowned in dirty data, and it can be very problematic. So I'll give you one example now. If we have time later, I'll give you a second example. Remind me about Uber later in their IoT example. I think the obvious example for a use case for Internet of Things is smart grids, smart energy grids. You know, the rise of renewable energy sources means things like wind power and solar power. And I know that solar power growth in the United States is tremendous, and it's beaten only by the solar power growth in India, which is growing at a much faster rate. The ambition for India growing solar power is just amazing. It's going to happen. But that means that energy grids have to be much more agile in how they deal with power consumption and production. If you have power coming from more than one source, if you have it coming from individual homes or rooftops, the grid has to be able to deal with that. So putting sensors at the generation place, which means homes, is important. And also you have a lot of devices generating and receiving traffic. But the opportunity is fantastic if you can take advantage of it. Here's the thing about the Internet of Things as I see it. It's all about the data. But like I said, the data, these things, they don't have very much in the way of brains. They have a lot of sensors. So they're like eyes and ears. They're like touch and smell. And they can report data, they can report telemetry, but they don't do much in the way of thinking. So the challenge we have is, how do we take the brains that we know from data center computing and marry it from this huge wash of devices that are generating valuable data if you know how to use it right. The data that can come from sensors, I wouldn't call intelligence. I think our challenge is to turn data into intelligence, and then from intelligence into knowledge. When you have knowledge, then you can take action. When you take action, you can make business decisions and make them faster. I'll describe an architecture that supports this transition from data to intelligence and intelligence to knowledge. Sorry about that. It turns out that in a three-tier IoT architecture, the three tiers we would describe are data center, gateway, and devices, device tier. A lot of the same concepts apply, a lot of the same attributes which are important in enterprise computing are necessary in the other two tiers as well. Just take security as an example. If we're talking about 3 orders of magnitude more things to manage, more devices on the network, your attack surface is much, much larger. You're potentially much more vulnerable to attack. So your security story is critical in an IoT architecture. You need to be looking at infrastructure that has a solid security story. Also, if you look at how you're going to manage those things, think about it this way. In a typical data center, our rule of thumb is with traditional data center operations techniques, you can have a ratio of 1:150, admins to servers being managed. And that's a lot. If you start using data center automation techniques, you can increase that, and that's one of the values of things like OpenStack. But if you're going from 150 things to manage to 150,000 things to manage, there's no way an admin can do that without extreme tooling and automation tools. So tooling to be able to handle the life cycle of these devices, all the way from deployment, maintenance, and update to eventual retirement is tantamount. You have to take care of that. And people are not going to solve that problem for you. Software. Well, it turns out we have a whole portfolio of software. You've been hearing about it all day. If you came into the forum today thinking of us as just a Linux company, I hope you'll come out of it thinking of us as a full software infrastructure stack. And if you look across the 3 tiers, you can see that we have a stack that we think is applicable. So common to all of them is our operating system product, RHEL, Red Hat Enterprise Linux, and the middleware platform, which is a pretty broad, one of the 3 broad middleware platforms out there. Java 2E-based middleware platforms, I should say. We also have a mobility platform that you've been hearing about today. And in addition to that, we have infrastructure as a service and platform as a service to help manage things at scale and develop things more quickly, as Jeff and Anuva were talking about just an hour ago. Since I have this on the slide, let me describe the 3 tiers. I hope they're self-explanatory, but we'll describe the transition from one tier to another. So the device tier, I'm just holding devices for you. These could be sensors on the jet engine. They could be sensors on train tracks or in signaling stations, and I'll give you a concrete example in a few slides. They could be things like my connected activity band, or the sensors in a phone, of which there are many. I think the iPhone has something on the order of 50 to 60 different sensors. There's a temperature sensor, humidity sensor, GPS, right? There's the camera, there's all kinds of things in it that can potentially report data. All of these generate a huge amount of data, even for one device. If you were to send all that data over to the data center, as Ranga had mentioned earlier today, or in the keynotes, you just won't be able to deal with it. So you need to be able to take the data from the device tier and rationalize it and do some pre-processing of it so it becomes more manageable. And that defines the transition from the device tier to the gateway tier. The gateway tier, or some people call it the aggregation tier, is exactly that. It aggregates data from the devices and simplifies it. So what characterizes the devices here is no single operating system, no single messaging protocol for communicating data, no single type of data. It's just a wide variety of everything at scale. The gateways tier's purpose is to help reduce that complexity, to cleanse the data, and as I said before, turn data into intelligence so that you can use it. There's a little bit more that happens in this translation as well, which I'll get to in a couple of slides. Going from the gateway to the data center tier is about taking that intelligence and turning it into knowledge. And the data center tier is something we know very well. Relational databases, Hadoop clusters, BIDW tools, all the tools that we who run data centers are very familiar with, and the business logic that goes there. Getting them to understand new types of data can be difficult to do. And the purpose of the gateway is to do that mediation, to do that translation, take many types of data from many data sources and turn it to easily understood data from your traditional data center tools. So looking at it the other way, I believe Ranga had mentioned this earlier. From my standpoint, the point of the Internet of Things an IoT architecture that's divided into 3 tiers like this is that you're trying to push decision making as close to the edge as possible. The more decisions you can make at the edge, the simpler it becomes for you to deal with all the data, and also the faster you can go. So imagine heart rate monitors or an EKG. You go into a hospital and the devices there that are monitoring the telemetry of your body, if they're connected to the network, then ideally the sensors there who are monitoring your device, like monitoring your heart rate, if they can make at least minimal decisions about what that data means without having to go all the way to the data center, they can make decisions about whether you need help right now or make a quick top-level assessment about whether you're healthy or not, if you need help or not. So being able to have at least small amounts of decisions made at the device tier helps you go faster, and it saves time and processing power. I mentioned before that security is paramount, lifecycle management is paramount, and you probably already know this about Red Hat, but just in case not, I'll cover it quickly. SE Linux was something that was invented with Red Hat and the National Security Agency in the United States. It's military-grade security. The idea is to reduce the attack surface of an operating system, so make it much more hardened to attacks, much less vulnerable, and when a part of the operating system or a process running on the operating system is attacked, it walls off that part of that process from the rest of the operating system so that the attack space is contained and attacks don't spread to the whole OS instance. I think that's critical here. Red Hat Satellite is Red Hat's tool for doing maintenance of systems at scale. You put systems and connect them to a Red Hat Satellite server. Satellite can update the operating system images. It can detect patches that are necessary and take care of that for you, do reporting on them. That becomes critical when you get security vulnerabilities. When you get security vulnerabilities, Red Hat has a security response team that responds to, I think, 98% of the vulnerabilities we see within 24 hours. When you couple that kind of response time with management tools like Satellite, that means we can respond by getting patches from the community into our product and then out to your field of systems within a day, most of the time. I'm not going to spend much time talking about OpenShift or containers because I think Numa and Jeff covered it very well in the last hour. I think the point here is all about not just the acceleration of the administration of an IoT architecture, but acceleration of the creation of services and deploying them across the 3 tiers. That's the brilliance of container-based development and deployment and using OpenShift as your development environment. You can create applications faster. Containers allow you to make applications that more easily span across these 3 tiers. So a little bit more detail about the gateway. So I mentioned to you that the gateway is the key in a 3-tier IoT architecture that it mediates between the tiers on either side of it, either downstream of the devices or upstream of the data center. The thing about the intelligent gateway is that it's got a lot of tasks to perform. It's going to be speaking, the devices, these intelligent systems are connected to the network. They'll be using a multiplicity of networking protocols or messaging protocols. The gateway tier needs to be multilingual. It needs to speak many different messaging protocols potentially. So you need a messaging system that can do that. Also, you'll be dealing with multiple data sources from different kinds of devices. So enterprise data integration becomes important. That's part of our middleware platform, but we think that belongs to the gateway tier. Being able to collect and aggregate data from different sources and make one. At the same time, storage. The amount of data generated from the devices is almost unfathomable. And you can't transmit all of the data to the data center tier. There's a lot of processing that happens here on the gateway tier, so that means a lot of mid-level storage that has to happen. It's still an enormous amount of storage, probably too much storage for traditional enterprise storage boxes. Software-defined storage is a good solution to that problem. That use industry standard server class machines that generally come at a lower cost than purpose-built storage. And when you use open source based software-defined storage, your cost goes way down. So the bottom line is that you can store a lot more data here at this middle tier for a lot lower cost. We think that storage is a big play here and in the enterprise data center tier. There's a lot going on here. Let me talk about business rules. So remember my example about EKG, heart monitor, health data. If you have dumb devices, but you have a lightweight rules management system, you can write rules that talk about how to process the data from the devices and make very simple assessments. and either make decisions, likely decisions right then, or at least package up the data and use business rules to interpret that data, which you can send back to the data center tier. So we think that business rules engines are important here in the gateway tier as well, at least a lightweight business rules system. You may have a combination of business rules here that are a lower level, device level kind of interpretation, and at the data center tier, you're going to have business rules that are probably taking mid-level decisions and packaging them into higher level knowledge. This slide just speaks to my point about how you deal with multiple messaging protocols. Our the AMQP protocol is something that spans a bunch of operating systems and languages. It's not language specific. Our messaging product within the middleware portfolio can speak to many different types of messaging systems. So it deals with the diversity of the multilingual aspect of IoT that you'll be dealing with. This is another way of putting things together. If you're looking at the gateway tier and looking where middleware comes into play, let me back up here for a moment and say, I talk to a lot of people about IoT. We're talking to some of our partners, large and small. We hear from customers from time to time, and they think that the key to IoT is the operating system. Absolutely, the operating system is an important decision to make across these tiers, but I think more importantly, as I said, it's all about the data and how you transmit information from one tier to another. Transmission of information here means and network connectivity means messaging, and messaging is a middleware problem. So if you're thinking about the IoT, you need to be thinking, what's your middleware playing here? This is what I'm trying to say. When I'm talking about the gateway tier, I'm thinking the three main problems you have to solve are, how do you talk to your devices with your messaging platform? How do you connect multiple data sources into an intelligent, coherent manner that you can send back to the data center? This is enterprise service bus functionality. And then something I don't think I've really mentioned so far. You've still got a lot of different data sources, a lot of different views of data coming from the device tier. But the data center tier helps if you can look at it as one view on the data. Data virtualization is an important play here. It rationalizes multiple sources of data and makes it look like one aggregate form. It can really help save you on the data center side if the gateway is doing data virtualization. Yeah, so I've already mentioned this example of being able to take health-based data at the device tier, applying very simple rules to interpret it, sending that to the gateway tier, and being able to aggregate that data and then send it back up to the data center tier. So I won't go into detail here. This is just a diagram that shows kind of how it goes together. Responding in real time. So I mentioned you want to push decisions as close to the leaf nodes as possible. If you have decisions made by the devices themselves, that's great, but this little thing, this little band, doesn't have the ability to make decisions. What it can do is measure different kinds of activity and then send to this guy, which you might think of as a small gateway. If you look at the app that runs on this thing, it actually takes the data, tries to interpret it, and from the raw data, it tells me if I've been sleeping or if I've been running versus walking. It's using very simple business rules looking at the raw data to make some decisions about my activity for me. So on the app, all I see is a series of confirmations. I don't have to tell it when I was asleep. It says, hey, I think based on the raw data here, I'm making a guess based on my business rule that you were asleep from this time to that time. Is that true? So this is a case of the device and the gateway working together, lightweight business rules to interpret data in a way that saves me time and makes me have to do less thinking. And if I have to do less thinking, that means the data center too has to do less thinking. And overall, that makes your overall IoT system faster and more cost effective. The data center tier, I won't spend much time on because I think you're all familiar with that. The point of this slide is to say there's a lot going on here. Business analytics apps, your standard data sources, relational databases, OLAP queues, Splunk, data warehouses, etc. We all know these. Again, we have a broad portfolio of infrastructure software to take care of that. I'm not even showing all the portfolio of software here. Just a piece of it that applies to this environment. We have a term called the Open Hybrid Cloud. And the Open Hybrid Cloud refers to the phenomenon that what we see in customers these days. Customers are deploying their workloads on-premise, but increasingly we see customers also deploying workloads in public clouds. Sometimes they're telling the IT departments, sometimes they're not. But we see both of these happening at once. And we acknowledge that this happens more and more
There will be no single environment for customers. And if you want to deal with customer deployments in the future, you have to supply an environment that makes it as easy as possible for customers to span their workloads across on-premise and in cloud. Open hybrid cloud means that every deployment will be some combination of on-premise and in-cloud computing. IoT is no different. In the data center tier it happens, but if you look at the 3 tiers of IoT, you could think of the device tier as a completely different deployment paradigm, a physical virtual cloud device. And so we believe that you have to support an environment where workloads and processes are going to go across all of these. BTC. If you were in Ranga's keynote a little bit earlier this morning, you heard him talk briefly about the positive train control example in the United States. I'll give you a little bit more detail on the example. One of the problems that we have with the train system in the US is there are a lot of accidents, a lot of fatalities. And that's because there's a shocking lack of data that's available to train operators as they're going. You would be amazed at how many accidents happen because a train isn't aware that a switch is turned against it. So it ends up derailing. Or a train goes against a crossing, a car crossing, and isn't aware that a car is crossing. It slams into the car, kills the drivers, and hurts the train. That happens much more often than you would hope that happens. Well, the problem isn't easy to resolve, but it's straightforward. And what we did was we worked with Mediacom and others to get intelligent systems put on the rails, on the rail tracks themselves, on switching signals, on crossings, and on the trains. We instrumented all these areas of the train system, which gives you all kinds of things you can do. For example, network-connected switches on a gate can broadcast, oh, the gate is open, or the cars are crossing the gate, and they connect with the network, which connects with the central dispatch center, which knows which trains are within 2 miles of that crossing. So 2 miles ahead, a train operator can be told, 2 miles ahead of you, there's a crossing, and the gate is open, and people are crossing. If you wait until that crossing is within visual range, there is just way too much momentum going in that train to slow down in time. But with 2 miles of lead time, any operator can take care of that. Here's another example. Acoustic sensing devices on the rails can listen to the pattern of the sound signal that's made when a train is rolling across the tracks. And it turns out when a train's wheels or the track itself are starting to deteriorate, that acoustic signature will change. So you can see from the change in the acoustic signature from that raw data that something is about to fail but hasn't failed yet, which tells the train operators they can either go to that section of track and inspect it, or they can go to the train itself and replace wheels, which prevents accidents before they happen. This is just one of the pieces of magic from the Internet of Things, but in order to make that happen, you need devices out in the field, you need them connected to the network. They're unreliably connected to the network, so you need a processing tier that can take that dirty data, which is really life or death critical. You need to be able to process that, make that clean data so you can make accurate decisions. And this is what we've done in the US. As Ranga had mentioned earlier, this is now a US law to start implementing positive train control to all rail tracks in the US over time. Red Hat has been working with a lot of partners, a lot of technology partners in the space, and we're continuing to seek new partners to build a full IoT ecosystem. Why? Because there's no single technology provider that will provide the entire solution. So we're working with systems vendors, people who make servers, who make embedded devices. We're working with within vertical markets such as retail, energy, transport, logistics, and others. We're working with the primary software vendors in those industries, the ISVs, because they're providing important parts of the solution in their industry. We're also working with consulting partners and systems integrators, again, vertically organized, so that we can work with our role is to supply the infrastructure for a whole IoT ecosystem that's composed of many different companies. Again, there will be no company that provides the entire solution. It would be foolish for us to assume that there were. And so we want to work with as broad of ecosystem as we possibly can. We're an open source company. Open source is in our DNA, so of course we're always looking for open source components to an IoT solution. These are just some of the communities and standards bodies that we currently participate in that play key roles in an IoT architecture. We encourage you to take a look at these as well. If you're looking into IoT for yourself, you're starting to get involved, take a look at these communities, take a look at these standards bodies, and get involved. If you don't know how to get involved in open source communities, Talk to any one of us. Any one of us in Red Hat can talk to you about how to participate. That's what we want. We believe that if we participate in the community and we put value there, then everybody benefits. Our customers benefit, we benefit, our partners benefit, and everybody wins. That's it for me today. I'm going to be here the rest of the day. I think I'm standing between you and a break, so go take a break.